Again. Okay, it says recording in progress. Okay, so welcome. Today's lecture, to follow up from Lucas's lecture yesterday, will be about the Gelfand-Naimark theorem. And I forget if the statement of that theorem was given yesterday. It might have been, but it's a key result. It's kind of a motivating result, the theory of C-star algebras.
Hey,
And
Nick, just so you know, I didn't quite get there.
okay, sure. So I do have a statement of the theorem. And so, what is it? Well, the theorem is that so I have a formal statement written here, but essentially the idea is that you can think of commutative C-star algebras as being sort of the same as algebras of continuous functions, and we have to say vanishing at infinity on a locally compact Hausdorff space X. And the space X can vary, but for different spaces, we get different algebras, and those will be the same sort of as C-star algebras. So how do we make sense of that intuition? Well, um, let's say we start with a topological space, which we call X. We'll say it's a locally compact Hausdorff space. So you can think of it as like a space with nice enough properties. Well, when we have that, we can consider the algebra of continuous functions vanishing at infinity, and that'll turn out to have the structure of a C-star algebra. So, and a commutative one because all the operations are given pointwise, and multiplication pointwise is commutative in the complex numbers, which is where the continuous functions will take values. So, we'll get a continuous function vanishing at infinity an algebra of continuous functions vanishing at infinity for each space X that's commutative C-star algebra. So in that way, we take a space and associate to it an algebra. Now, this theorem is making sure we can go the other way, namely that if we start with a commutative C-star algebra, then we'll get via an isometric C-star algebra isomorphism some algebra of continuous functions vanishing on infinity on some space X. They're going to be like the same. So, what we'll end up with ultimately, and I'll touch on this briefly at the end, but not, I won't emphasize it. So you can have this association between spaces and their algebras. It turns out like certain maps between spaces, so continuous functions, will be associated to al maps between algebras and vice versa. That gets us a certain like sort of duality between spaces and commutative C-star algebras, and that's sometimes called Gelfand duality. But in that sense, you can think of like the algebras as corresponding to spaces and vice versa in the case that the algebras we're talking about are commutative. And so, one more remark I'll make at the beginning here is that sometimes you hear C-star algebras described as non-commutative topology, and the intuition is being that, well, what I'm describing here is kind of that the study of commutative C-star algebras is like we're essentially the same as the study of topological spaces, specifically locally compact Hausdorff spaces, so spaces with nice properties. And so when you extend to all C-star algebras, including non-commutative ones, then you're like extending the study of topological spaces to the setting of non-commutative algebras. And with that, like that's kind of a motivating principle that people refer to when they call C-star algebras a non-commutative topology. So I mentioned, we're talking about here algebras of continuous functions vanishing at infinity. I've written a formal definition of that down on this slide. Just to remind everyone, we're talking about complex valued functions here, so valued in the complex numbers. We want them to be continuous, and the vanishing at infinity part means they satisfy this property where given any epsilon, we can take a compact subset of the space large enough that once we get outside of that subset, the size of f, the modulus of f, is going to be smaller than epsilon. So that's to say that we can take compact sets large enough that when we get outside of that set, the function can be made arbitrarily small. And that gets us here. When we do that, we can consider a norm on this algebra, namely the supremum norm, where we take the supremum of all moduli of the function over different points. And we can give it an involution, the star operation, by pointwise conjugating functions. That's a complex conjugation of numbers. And so I've written it down here as an exercise to show that every commutative C star algebra, in fact, um, takes this form. No. That's our goal. That's our goal. But as an exercise, you can show that just when we start with such an algebra, that's indeed a C star algebra. So there are a lot of things to check there, but yeah. So again, this exercise here is to verify that when we take a space X, we get a commutative C star algebra. And the goal of this lecture is to show that we can go the other way. If we have a C star commutative C star algebra, we can get a space that it's associated to. By the way, I think some of you have joined the goals Discord. I think I'll go ahead and send these slides later on to the goals Discord so you all can review them. And again, the lectures will be on YouTube once they're all uploaded. Okay, so how are we going to construct this space? Well, to start off, we're going to recall this definition from functional analysis, the weak star topology. I believe it's in the preliminaries. But if we have a dual space, so the continuous linear functionals in some, let's say a Banach space, so complete norm vector space, we can look at the topology of pointwise convergence, and that's the weak star topology. And I have it written down here explicitly in terms of a standard basis of open sets, but the principle here is that if you have functions like a net or a sequence, those functions converge to a specific other function if and only if the functions converge pointwise at every point of the domain that the functions all share. So we fix any point in V, and then if we get convergence of this net of functions at that point, then and the point was arbitrary, then we get convergence everywhere. And I made a note here, you can compare that to the SOT topology we discussed earlier on von Neumann algebras, the strong operator topology that is. That's also the topology of pointwise convergence, except there we're considering operators on uh, a Hilbert space, and then the domain of the functions is the Hilbert space. All right, so that's the topology. So we're going to start with here with a subset of a dual space of the C star algebra A. And we're going to consider the weak star topology on that subspace. Well, I said subspace, but I should say subset. It's a topological subspace, but really it's just like a set of certain linear functionals. That's what our space is going to be. That's the space we're going to use for locally compact Hausdorff space. And so, A is it's a Banach, a C-star algebra is always a Banach algebra. In particular, it's always a Banach space. And we can consider its dual space A star. Now, if phi is an A star, we'll say that phi is a character of A. If it's first of all, it's non-zero, so it's not everywhere vanishing. And also, if for all A and B and A, we have phi of AB equals phi of A times phi of B. In other words, we can say phi is multiplicative. So in that sense, we can say that the characters are all non-zero multiplicative linear functionals. Now, we're not saying it preserves an involution between A and C, but it'll actually turn out to be a consequence of these assumptions that it does, and that'll be proven over the course of this lecture. So, oh, by the way, interrupt me anytime if you have questions, I'm happy to answer. Okay, back to where we were. So we'll let A hat as a subset of A star denote the set of characters inheriting the weak star topology from A star. And A hat will be our locally compact Hausdorff space. We'll show that it is indeed one such space. We'll call A hat the spectrum of A. Now, there's I have kind of like an algebraic aside here about another way that we can interpret the characters or the spectrum of A. So suppose that A is unital, that is, has a multiplicative identity element. Well, here's a general definition, kind of an algebraic definition. If we have a commutative algebra, we'll call it B, then an ideal I in B is a vector subspace of B such that for all elements A in the subspace, you can take any B anywhere in the whole space, anywhere in the whole space B, multiply it by A, you get something in I. So it kind of like absorbs everything in B under multiplication. That's the idea of an ideal. And I say I triangle B, the notation there is I is an ideal in B. That's like some notation that you sometimes see in algebra. Given an ideal, one may consider the quotient algebra B mod I. What do I mean by that? Well, there's the standard quotient vector space construction. B mod I is going to be that quotient vector space. And when I is an ideal, so you can convince yourself that this space will also have the constructor of an algebra inherited from B. So we can talk about the quotient algebra. Now, there's the following theorem called the Gelfand-Mazur theorem. I won't prove it here, but it's in some standard resources on Banach algebras. If B is the unital algebra over C, such that B is a field that is all non-zero elements are invertible, then there's a unital algebra isomorphism B to C. So once you've checked that everything is invertible in the algebra, you're going to get, it's actually going to be the same as C. You'll get like an isomorphism of algebras. So it's an interesting fact. The proof I've seen for this uses complex analysis, but it might be easier if you already assume B to be commutative. It turns out that you could assume B is non-commutative, but then you prove it's commutative anyway via this isomorphism from B to C. And this theorem is going to be used a lot to establish the foundations of what are needed for the Gelfand-Naimark theorem. Well, actually, at least in terms of the interpretation of the characters as maximal ideals, it's a relevant theorem. So, and I used the term maximal ideal just now. What does that mean? It's an ideal which is maximal among proper ideals. That's to say that it's an ideal, it's a proper ideal such that it's not properly contained in any other ideal. So if you have an ideal containing the maximal ideal, it's to say that that ideal is either equal or it's the whole vector space. It's the whole algebra. And maximal ideals turn out to be the same as ideals whose quotients are fields. This is sort of an algebra fact. A corollary to the Gelfand-Mazur theorem then goes as follows. If A is unital, then there's a one-to-one correspondence between A hat and the maximal ideals of A. And I've written here how we get that correspondence. So in one direction, you take a character. Well, by the first isomorphism theorem, from algebra, which applies here, that character is going to induce an isomorphism between A mod, the kernel of phi, which is an ideal, and the image of the character, which is C. And because you have that isomorphism, particular C is a field, it ends up being the case that kernel is a maximal ideal. So from a character, you get a maximal ideal. How do you go the other way? Well, you start with maximal ideal. You can consider the quotient map from A to A mod I. That's a map between algebras. When you associate A mod I to C via the Gelfand-Mazur theorem, that ends up becoming a character. And so this is one map is the inverse of the other. We get this one-to-one correspondence. And as such, we can think, if we want to, of the spectrum of A as having points which are maximal ideals. Like you can think of the characters as maximal ideals if you feel like it, because there's this one-to-one correspondence. Now, I don't know if I'll be using this in the rest of the lecture, but I'm going to make a remark here that you might wonder, because we talked earlier about the unitization of a C-star algebra. You might ask, how do the characters of the C-star algebra compare to the characters of the unitization? Well, they're actually very closely related. In fact, they're almost in one-to-one correspondence. What you can do is you can take any character in A hat, you can extend it to a character of a twiddle, the unitization, by having it map like a scalar lambda to scalar uh, lambda, or to lambda and C. Yeah, so there's like a natural way to extend it. It turns out you get a character that way. And then there's one more way you can get a character on a twiddle, the unitization. That's you start with the zero homomorphism, the zero map. from A to C on so we define the zero linear functional to not be a character, but you can still extend that to a character of a twiddle by having, again, like scalars lambda go to a lambda and C. That becomes non-zero, and that's the other way you can get a character in a twiddle. So there's this almost one-to-one correspondence. Well, there is a one-to-one correspondence between a hat of, or a hat, a twiddle hat, I guess, and a hat union phi zero, where a hat union phi zero, and I'm using the notation phi zero is the zero map. So, a hat union phi zero here is the set of multiplicative linear functionals of A. So in the rest of this lecture, like I have that written down a lot, a hat union phi zero, but I might refer to it as the set of multiplicative linear functionals of A because that's the same thing. Now, the Gelfand-Mazur theorem is relevant here, actually, and this is going to be used in the actual proof of the theorem. So by an application of Zorn's lemma, an additional corollary of Gelfand-Mazur shows that we can recover from A hat the spectrum sigma of A of any element A in A. And what is it in particular? Well, I'm assuming here that A is unital. And spectra, when you could like pass the unitization of a, well, okay, well, okay, but when you talk about the spectrum, you're talking about it in terms of unital algebra because we're talking about when like lambda minus the element is invertible. So let's say we're in the context of unital algebra. Well, for all A in the algebra, the spectrum of A relative to that algebra is going to be the same as the image phi A for all characters phi. So what does it mean when a complex number is in the spectrum of A? That's the same as saying that there exists some character phi of the algebra such that phi of A is that number. It's going to be the same thing. And I am going to prove that here. So proof. If an element A, let's say an element A is invertible, so that's prove one direction here. Then for all phi, well, here's a fact about characters that I haven't written down explicitly. Characters are non-zero multiplicative linear functionals. It turns out those will always be unital. They'll be unital in the sense that they map one to one. And you can sort of like convince yourself that that's true. So if we have phi a character, we'll have that 1 equals phi of 1, which equals phi of A times A inverse, which equals phi of A times phi of A inverse. So what are we seeing here? We're seeing that phi of A, you can multiply by some complex number and get 1. That means phi of A is non-zero. So if we have an invertible element, that means that phi of that element is going to be non-zero. And just like kind of this condition on elements being invertible versus how their characters behave on them, we can go the other direction. We can say, let's say we have a non-invertible element, A. And I'm going to use the technique from algebra here where we use Zorn's lemma to establish the existence of a maximal ideal. That's something you may have seen in ring theory if you've taken algebra courses, and it works here too. So if A is non-invertible, then the ideal A times A. So you have this set of everything that's a multiple of A in the algebra. Little exercise is to check that that's an ideal. It's going to be a proper ideal from A, which is precisely to say that A is non-invertible, as we've assumed. Now, let's consider all the proper ideals of A. What I actually should have said here is consider all the proper ideals of A containing the element A. That's the partially ordered set that I should have been continued written that I should have had written down here. But you consider all the proper ideals of A containing the element A. That forms a partially ordered set in the sense that they're partially ordered by inclusion. So one smaller than the other if one is contained in the other. And it satisfies the hypotheses of Zorn's lemma in the sense that if you have a ch increasing chain of ideals, you can take their union. That's also a proper ideal. Why will it be proper ideal still? It's because it won't contain the element one. If one is in an ideal, then the ideal has to be everything. Therefore, a proper ideal can't contain one. And so if you union proper ideals, you'll get like another thing that's proper. So, okay, Zorn's lemma conditions are satisfied here, which implies that A times A is contained in a maximal element of the poset, that is a maximal ideal. And so we know now that the element A is in a maximal ideal. Now, let's call that maximal ideal I. Well, now we can consider the quotient map from A to A mod I, which can be identified with C by the Gelfand-Mazur theorem. And that gets us a character from A to C. For the corresponding character, we'll have phi of A equals 0 since A will be in the kernel. And so what have we established here? We've established that an element A in the algebra is invertible if and only if for all phi of A is non-zero. That's what we have here. Now, when we talk about the spectrum, we're concerned about the invertibility of elements phi or phi times 1 minus A for a complex number lambda. Or I think I said phi times 1. I meant lambda times 1 minus A. So given an element A for all lambda and C and for all phi and A hat, we can use again that phi is unital and maps 1 to 1 and see that phi of lambda times 1 minus A equals lambda minus phi of A. And for all by the previous, we know then that phi, or not phi, we know then that lambda minus phi of A is in it's going to be non-zero for all phi if and only if lambda times 1 minus A is invertible. So this is to say we have 0 equals lambda minus phi of A for some phi, that is phi of A equals lambda, if and only if lambda times 1 minus A is not invertible. And this completes the proof. This tells us that lambda is in the spectrum of A if and only if for some phi we have phi of A equals lambda. That completes the proof of this theorem right here. That, well, it's written on the top too, I think, that, what does the spectrum look like? It looks like all the images of that element on characters. Okay. So, theorem here. Here we're going to we're going to do some general topology. If you're like me and you like general topology, then you'll be excited. Uh, I like topology. So the space A hat union phi 0, which is the space of multiplicative linear functionals. So we're giving that the weak star topology from A star, the dual space. We're going to be establishing that this space of multiplicative linear functionals is a compact Hausdorff space, and from there we'll establish that implies that A hat is a locally compact Hausdorff space. We'll further make the note that the space A hat is compact if A is unital. So to start off, well, we need A hat union phi 0 to be Hausdorff. What does that mean? It means it separates points. If we have 2 points, we can make open neighborhoods around them that are disjoint. And well, if we take a topological subspace of a larger Hausdorff space, we end up with a Hausdorff space. So the weak star topology, you can convince yourself is Hausdorff. A hat union phi 0 inherits the weak star topology. It's a topological subspace, and therefore it has to also be Hausdorff. So we get a Hausdorff topological space. Now, we have to prove compactness. So we're going to start by showing that the it's a hat union phi 0 is a subset of the closed unit ball in the norm on A star. Why does that help? Well, I think so. Ekin, who's in this program, is Turkish, told me it's pronounced Alaolu, I think. I always wondered, but Alaolu's theorem. Yeah, I think that's the rough pronunciation. It's roughly correct. Um, so that theorem tells us that the closed unit ball of in the closed unit ball of a dual space of a Banach space is compact in the weak star topology. So once we can establish that all the multiplicative linear functionals are in the closed unit ball, we'll be able to establish that's a subset of a compact set in the topology. What can we do? So why does that help? Well, then if we're able to show that it's a closed subset of that compact set, it's closed in larger space, then it has to be compact as well. And that'll be the method we're using here. So first establish it's in the unit ball it's on this slide, I'll explain it. And then establish that it's closed, therefore compact. Now, so let's take a multiplicative linear functional phi. So in A star, we think of as a norm space with like the standard norm, which is like the operator norm on B of H, or by skit. And when we do this, it ends up, you can convince yourself that norm of phi is greater than one, if and only if for some A and some element A, we have the norm of A less than one and that phi of A equals precisely one. So we do there is we take an element such that phi makes the norm larger, and then we scale it in a way, we rig A in a way where like it satisfies these properties. So if we want to prove that um, norm of phi is less than or equal to one, it's enough to establish that there does not exist such an A. So let's take some, again, multiplicative linear functional phi. Let's say we have an element A with norm less than one. Well, then the spectral radius, this is a fact from spectral theory, spectral radius is smaller than norm of A, which implies in particular that one is not in the spectrum of A. That's to say that 1 minus A is invertible in A. That is, phi of 1 minus A is non-zero for all phi in A. But then using that phi as unital, we get that phi of A can't be equal to 1. So we can't get that element A with norm less than 1 such that phi of A equals 1. There exists no such element. And that tells us that the norm of phi is smaller than 1. So the multiplicative linear functionals, A hat union phi 0, are in the closed unit ball of A star, which by Alaolu's theorem is weak star compact. So therefore, it'll remain to show that A hat union phi 0 is weak star closed in A star, since a closed subset of a compact set is compact. Now to this end, suppose we have a convergent net in A hat union phi 0, converging to some phi in A star. So we don't know where phi is in the dual space, it's just somewhere in the dual space. Well, um, we to check that it's a multiplicative linear functional, well, we just have to show that phi is multiplicative. And indeed, we get that by definition of the topology because all the pointwise convergences hold. We can pass the limits pointwise. We get that phi of AB equals phi of A times phi of B for any A and B. In other words, phi is actually in A hat union phi 0. So A hat union phi 0 is closed. Therefore, putting everything together, it's a compact Hausdorff space. Now, A hat, it has the weak star topology inherited from A star. We can also think of that as the weak star topology inherited from A hat union phi 0, since that inherits its topology from A star with the weak star topology. And if we remove, so, A hat you can think of as getting its topology from A hat union phi 0. So it's like we've taken A hat union phi 0, which is the space, we've removed one point, which is phi 0. And if we remove one point from a compact Hausdorff space, that always results in a locally compact Hausdorff space. It's like a general topology exercise to check that. Therefore, A hat is going to be a locally compact Hausdorff space. Now, there's one more thing to establish, which is that the space A hat is compact if A is unital, and we'll do that here. If A is unital, we have again that the characters are unital, which separates phi zero from all phi in a hat in the weak star topology. Why is that? Well, we have all the characters. The characters all take the one element to one. But then we have this phi zero. It's going to take the one element to zero. And because they like, and that separates phi zero from all the characters in the weak star topology. That is to say that phi zero is an isolated point in a hat union phi zero. And it is also a fact that if we remove an isolated point from a compact Hausdorff space, we end up with another compact Hausdorff space. And that gets us that A hat is compact if A is unital. And this completes the proof of the theorem. And in this process, this is some more general topology stuff, but this proof realizes A hat union phi zero as what's called the one-point compactification of A hat. And that's this process where you take a locally compact Hausdorff topological space. You want to make it compact. Well, you can do that by adding one additional point to the space and defining a certain topology. And I'll just briefly describe what that is. The open sets without the point are the same, but a set containing that point is open if and only if the complement is compact in the original space. That's the one-point compactification of a locally compact Hausdorff space. And it turns out that if you have a compact Hausdorff space, you remove a point and then you add it back in. That's you get what you start with, and that's going to be the same as the one-point compactification of the space with the point removed. And so this proof establishes that A hat union phi zero is the one-point compactification of A hat with all the relevant topological properties. Now, we're going to define now the Gelfand transform. We're going to define what the map is between that identifies A with the continuous function vanishing at infinity of A hat. So we're going to start by defining a slightly different map, gamma zero, from A to the C of A hat union phi zero. How are we going to do that? Well, let's say we have an element A and A. Where is gamma zero going to take A? Well, it's going to take it to the continuous function that takes any character phi and evaluates it at A. So gamma zero of A of phi equals phi of A. And that's going to be indeed a continuous function. Why is that? Well, because we have well, the pointwise continuity stuff. We're dealing with the topology on A hat union phi zero, pointwise convergence. And so that gets us that limits past the limits when we in gamma zero of phi, gamma zero of A, I mean. So gamma zero of A is going to be continuous indeed, which gets this to be a well-defined map. And since the elements of A hat union phi zero respect addition, multiplication, and scalar multiplication, so because they're multiplicative linear functionals, well, we know that's true. We also know that these operations are defined pointwise in the space of continuous functions, which means ultimately that, and you can kind of check this, review this, convince yourself. Well, we get from here that our map gamma zero from A to the continuous functions of A hat union phi zero is a multiplicative linear map. And so from here, well, what we want, for this theorem is an identification between A and C0 of A hat. And just by modifying this a little bit, we can get that. Well, we know you can check here that given any A, gamma of A of phi zero equals phi zero of A equals zero. So since that means that since A hat union phi zero is the one-point compactification of A hat, we're able to naturally identify C0 of A hat with the star subalgebra of C of A hat union phi zero, comprised of all continuous functions vanishing at phi zero. And by the way, this gives some like topological justification for why we call C0 continuous functions vanishing at infinity. It turns out if you take the one-point compactification of the underlying locally compact Hausdorff space, then you end up being able to identify C0 with the actual continuous functions of the larger compact Hausdorff space vanishing at the specific point that you add in. And when you add the point in the one-point compactification process for topological spaces, you sometimes call it the point at infinity. And there's motivation for that from like other areas, topics in math. But you add in the point at infinity, and then what you do when you look at the continuous functions is you realize in that setting the C0 as the actual continuous functions vanishing at the point at infinity on the one-point compactification. But what I'm kind of alluding to here is that we're able to identify C0 of a hat with the subalgebra of C of a hat union phi zero comprised of all continuous functions vanishing at phi zero. And the image of gamma zero is in this subalgebra. I should have written at the top gamma zero of a of phi zero equals phi zero of a. So we're still dealing with gamma zero, but we're ultimately defining here gamma. So because everything in the image of gamma vanishes at phi zero, we end up being able to obtain a multiplicative linear map via identifications, which we denote gamma, where gamma goes from A to C0 of A hat. And what's the definition through all this? Well, again, things are set up in this way where gamma of A of phi always equals phi of A. So we have an element A in the algebra. Where does gamma take A? It takes it to the function that evaluates characters at that element A. Um, and as a remark here, we have that previous theorem that the spectrum of an element in a unital algebra, at least, is the same as the image of the element and all the characters. And we can translate that here into the context of this function by gamma by saying that for all A, the spectrum of A is equal to the image of the continuous function gamma of A. So, we have an element A. What does gamma of A looks like? Well, it evaluates A at all the different characters. So if we want to take the image of gamma A as a continuous function, it's the same as its image on all the characters, which is the same as the spectrum of A. So we take the image of gamma of A, it's going to be the same as the spectrum of A. And again, I've been describing everything here, like gamma zero here and gamma A and gamma as multiplicative linear maps, but we haven't yet established that gamma is star preserving. So we'll be able to do that now. And we need one more lemma. Well, the lemma here, if A and A is a self-adjoint element, which is to say that A star equals A, then the spectrum of A is going to lie in the real numbers. So it's going to be a subset of the reals. And there's some power series stuff that we're able to do to prove this here. So let A be a self-adjoint element. Well, given a real number t, we may define an element exponential of it of A by the usual power series formula. That's going to be an element of A. Why does that make sense? Well, for the usual power series formula for the exponential, it's absolutely convergent. We get absolute convergence in A as well. And because A is complete uh, and so multiplicative in norm and all that, we end up getting a well-defined element in the algebra A. And what happens if we apply the star operation to the element we get? Well, because the involution is additive and or it's like it's conjugate linear and like sort of reverse multiplicative. We can combine, and because also it's continuous, the star operation is continuous, we can apply it term-wise to the power series to see that by this power notion of like exponential in the algebra, well, star of exponential of ITA is going to be equal actually to exponential of minus ITA. Now, how does exponential of ITA compare to exponential of minus ITA? Well, in, complex analysis, we have the rule that e to the a times e to the b equals e to the a plus b. That can be shown used by manipulating power series. And we actually get the same rule here because it's just like works out the same way. If we multiply exponential of ITA by exponential of minus ITA, we just take the difference of ITA with itself. We get exponential 0, that's 1. Uh, so, oh, I guess I haven't, I guess I should be assuming here that A is unital. And usually it's fine when you have to like deal with a unital algebra specifically because you pass the unitization. I probably should have been more careful about that here, but for the power series to make sense, you want a unital algebra. And well, I guess when you're checking the spectrum, it's always in the context of being in a unital algebra or in the unitization of your given algebra. And so, this exponential map, it's well defined in the context of the unital algebra containing the element, and it all works out. And in that setting, we can talk about unitary elements because you can talk about when an element, when the adjoint or the star of an element is the same as its inverse, or so that multiplying by this a star for the element A gives you 1, the unit. We've shown right here that exponential of ITA is indeed unitary. So when we take star the exponential of ITA, we get the inverse of exponential of ITA. So exponential of ITA, this element here we've defined with the power series, that's going to be a unitary element of the C star algebra. Now, what do we know about unitary elements? We know from the last lecture, I think, that their spectra has to be on the unit circle of C. So everything in the spectrum is modulus 1. Now, let's say we take something in the spectrum. Uh, what, well, that's the same again as saying that that number is in the image of the element exponential of ITA on some phi for a character phi. Now, what do we know about characters? They're continuous, linear, and multiplicative. So let's say we want to take phi of exponential of ITA. Well, we can look at the power series. We can we can like apply phi termwise by continuity. We can use multiplicativity to see that phi of exponential of ITA is actually the same as exponential of IT phi of A. So since exponential of ITA is unitary, what we get here is that the modulus of exponential of IT phi of A is 1 for all t. I should say here, by the way, when we pass over to exponential of IT phi of A, when we talk about the exponential, I mean the usual exponential and complex numbers, because IT phi of A is a complex number. And so we've like kind of translated the power series over from the algebra to the complex numbers where we can take power series. Um, and so for the usual exponential and the complex numbers on IT phi of A, we get that its modulus is 1. We can say that for any t. And it turns out, you can check this, that when we have these conditions, it implies that phi of A is a real number. We can let phi be any number that's real, phi, or not phi. We can let t be any arbitrary real number. T is just any real number. We can move it around, and no matter what, we're going to get that the exponential of IT phi of A has modulus 1, and that amounts to saying that uh, actually that the imaginary part of phi of A equals 0. That's the same. That's how this works out. So the conclusion from all this is that phi of A is in R, the real numbers, and this completes the proof that the spectrum of A is in the reals. And that's actually going to be relevant here for the Gelfand-Naimark theorem in showing that characters and ultimately the map gamma are star preserving. So what I have on this slide was actually covered pretty much in Lucas's lecture. And by the way, right over here, there should be a star. There should be a star here. It's a mistake. So, but I mean, I'll just summarize what's on this slide. Well, this slide is the argument shown previously in the other lecture that if you have a map that maps self-adjoint elements to self-adjoint elements, then it has to be star preserving. Now, so what can we say about a character? Well, its image on any element is in the spectrum of that element. Let's say we have a self-adjoint element to the algebra A. We apply phi, some character, to that element. We're going to get something in the spectrum that's a real number. What are real numbers? Well, real numbers are the same as the self-adjoint elements of the algebra of complex numbers. So our character is phi. They're actually going to be, they're going to map self-adjoint elements to self-adjoint elements. And since phi is a linear map and all that, that's the same as saying that phi is star preserving. Now, since the star operation on C0 of A hat is defined pointwise, the Gelfand transform from A to C0 of A hat has to also be star preserving. That is, it's a star homomorphism. So now we have that gamma satisfies all the algebra homomorphism properties that we'd want it to. It's additive, scalar multiplicative, and preserves the star operation. So we have one more thing to do here. We have to establish that gamma is an isomorphism. So it's a one-to-one correspondence. And we'll be able to establish also here that it's isometric, although it turns out that any isomorphism of C-star algebras actually has to be isometric. In spite of that, we'll be proving first that's isometric. In this case, in the case of this proof, the fact that gamma is isometric is actually going to tell us that it's the map is an isomorphism, and that's how we'll do our conclusion here. Why is that? Well, I have written on the slide right here, I have that the image of gamma separates points in A hat. Why is that? Because characters are different if they evaluate differently on some element, and that ends up being the same as the image of gamma separating points in A hat. We also have that the image of gamma vanishes nowhere on A hat. Why is that? It's because the characters are non-zero by our definition. And when we have these two conditions, the general Stone-Weierstrass theorem for continuous functions implies that the image of gamma is a dense star subalgebra of C0 of A hat. Therefore, to show that gamma is an isomorphism, it will be enough to show that gamma is isometric. Why is that? Well, an isometry is always injective because points with positive distance get mapped to points with positive distance. Or I said isometric, and isometry is always injective. That's what I meant to say. It's always an injective map. Now here we have that the image of gamma is dense in C0 of A hat. And if the image of an isometry is dense, it's actually all of the space. And what I'm using here when I say that is that the domain is complete. It's a complete metric space. So if you want to hit just an arbitrary point in the codomain, you can approximate it by points in the image, and then those points end up being close together in the domain, and we get something that maps to within the codomain. So just using the fact the image is dense and the properties of all the algebras we have here, it will follow that gamma is an isomorphism if we can prove that gamma is isometric. So this is almost the last slide. This is where we conclude the proof. So let's start by considering a self-adjoint element so we can use our lemma. Recall from, I think, the previous lecture, maybe the preliminaries, that this implies that the norm of A equals the spectral radius of A. Well, since sigma of A is in the image of gamma of A, we have by definition of the supremum norm and by definition of the spectral radius that the norm of A is actually going to be equal to gamma of A norm. So gamma is going to be norm preserving on self-adjoint elements. And that turns out to be enough because for general element A, recall the C star identity, where the square of the norm of A equals the norm of A star A. And in particular, you can notice that A star A is self-adjoint. So by putting all that together and the fact that gamma is a star homomorphism, we have that the norm of A squared is actually going to be equal to the, or we have that the norm of A is actually going to be equal to the norm of gamma A, because their squares of those norms are equal. And that proves the Gelfand-Naimark theorem. So that's basically everything I had. I have one more slide here with some further remarks. One remark, note that if A is unital, then A hat is compact. Therefore, we get actually an equality between C0 of A hat and C of A hat. So we end up with an isometric isomorphism between A and just all the continuous functions complex valued of A hats. Now, another comment, I alluded to this earlier on, but a duality emerges between locally compact Hausdorff spaces and commutative C-star algebras. And likewise, a duality emerges between a compact Hausdorff spaces and unital commutative C-star algebras. I referenced this page on NLab on Gelfand duality for details. If you don't know NLab, it's this website about math where like everything is in terms of category theory. So you get like a lot of category theoretic exposition over there, if you know what that is. But that's relevant to Gelfand duality. Why is that? Well, it's because these dualities can be understood as contravariant equivalences of categories. What happens is spaces, locally compact Hausdorff spaces, for instance, will correspond to commutative C-star algebras. If you have a certain type of map between those spaces, you'll get a map going in the other direction on commutative C-star algebras. Why is that? Well, that's to say that like a map from space X to space Y will end up giving you a map uh, from continuous functions of the space Y to continuous functions of the space X. So the map sort of reversed the direction they were going in. And those correspondences between maps will preserve composition and all that. We get what's called a contravariant functor, and it'll be what's called full, faithful, and essentially surjective, the last part being what is established by the Gelfand-Naimark theorem. And so you can consider all the spaces in their maps together as being sort of the same as all the commutative C-star algebras in their maps together. That's called like what's what you could consider duality in the setting of category theory. And so the upshot of that is that, we can think of the study of spaces with nice enough properties in their maps as being the same as the study of commutative C-star algebras in their maps. And again, there's this principle that C-star algebras are the study of non-commutative topology, where we take the study of spaces, extend them to the study of non-commutative algebras by looking at all C-star algebras. And then we can apply maybe some intuition that we get from topology to this larger algebraic setting where C-star algebras are dealt with. A final note here, which really gets beyond the scope of goals, is that there's an analogous situation that arises in algebraic geometry. Why is that? Well, I've made some commentary about how you can think of the characters as maximal ideals. So we're representing an algebra, the C-star algebra commutative, over its a structure on its underlying space of like maximal ideals. And this predates the construction referred to here on the slide in algebraic geometry, but there's an analogous situation there that provides the foundation for like most of like the structures on which the structure on which modern algebraic geometry is done, where in that setting, you can take any commutative ring, associate to it a spectrum of prime ideals, there it's prime instead of maximal, and give it got spectrum, a certain structure, which is known as an affine scheme. You get then a duality, contravariant equivalence of categories between commutative rings and affine schemes. You can extend that to get general schemes, but really like the seeds of that whole idea uh, are seen here in the maximal ideal setting and in the Gelfand-Naimark theorem. So, it's part of a larger kind of like sort of perspective in math. And this is, you know, provides some motivation, intuition for a lot of different things you'll see in other areas. And that's that. I guess my talk ends here. And I'll answer any questions. I don't know if I should stop recording. Should I do that?
Yep. Thanks, Nick.
All right.